Are you guys ready for video number 11? We're getting towards the end. Yay! Okay, this is a doozer for a lot of people. You could go to a lot of colleges and maybe not even hear this word mentioned. Kind of more popular back in the olden days. Yeah, people would just rather use molarity and other things than normality. Normality, I call the evil cousin of molarity because they're similar, but this term that we use, equivalence, is a little wackadoo for a lot of students and hard to grasp because even moles, when we first introduced moles, that was a tough concept for a lot of students to grasp until you relate it. It's just an amount, right? It's like a dozen is 12. A mole is 6.022 times 10 to the 23rd. It just gives you a number of particles. And we can relate that to grams and whatnot. So we can get a grasp of it, wrap our minds around it. But equivalence, it's a little weird. So normality is similar to molarity. Molarity is moles of solute over liters of solution. Whereas normality is not moles, it's equivalence of solute over the volume of the solution in liters. So instead of moles per liter, you get equivalence per liter. You'll see EQUIV or EQ for equivalence, and that's given the term capital N, just like molarity is capital M. So normality, molarity. Normality, we'll see on the next board, is really stems from more acid-base chemistry back in the old days. It's quite useful. It's a nice little shortcut we're going to use. Little arrow in your quiver. You don't have to pull it out all the time and shoot that arrow. We're going to get to molarity as much as we can, but it's really useful in some scenarios for acid-base chemistry and some redox chemistry. But let's see if we get this concept of equivalence down, and I'm going to try to hit you with it in the most simplistic way possible. I'm not going to get fancy pants on you. So an equivalent is not necessarily an amount like a mole is. A mole is a certain number of particles, right? So an equivalent relates to how reactive a substance is. So we'll see that when we look at acids and bases in a little bit. I don't know if I'll get into redox, maybe just acids and bases. So what I'm finding for students is they're grasping moles now. Equivalence is weird. So what we want to do is we want to get from equivalence to moles as fast as we possibly can. All right. If we're in equivalence, let's get out of it and get to moles. So rather than going through what a lot of textbooks talk about as far as equivalent weights and all these other things, all I'm going to do is just show you how to take the chemical formula of a species. And we're going to define 1 mole of that species, right? Let's say we have 1 mole of that species exactly. How many reactive portions or parts are there? That'll be the number of equivalents. And that allows us to convert equivalents to moles. And it's from the chemical formula. So when you know the formula, it's actually pretty easy. We can get from equivalents to moles quite readily. So we're going to connect equivalents to moles using the chemical formula, like I said. Assume exactly 1 mole of that substance, and then determine how many reactive parts or portions there are, and different for acids and bases, and different for oxidizing agents and reducing agents. So let's talk about those in turn. I'm not going to get to the redox. I haven't introduced that topic yet. So we will focus just on acids and bases. It's going to be a little hard at first, but hopefully you can start to see the trend and the pattern of converting equivalents to moles. And then we're good with stoichiometry. We'll be able to pop this into unit line equations for stoichiometrical work with chemical reactions. Be right back. Let's take a look here. Equivalents make more sense when you're looking at a specific substance because we're looking at reactivity, not amount. So normality equivalents, you can almost think of them as specialty or very specific concentration units geared towards acids and bases. I've seen some people, again, use them for redox reactions with oxidizers and reducers, but we're not going to get into that. We're just going to stick with acids and bases at this level. So let's look at acids first. I think they're easy. And then we'll look at bases. We'll define how they react. And then we'll look at the chemical formula and determine, well, how many reactive components do they have? So what we're going to do if we have an acid, and then again, an acid has an acidic hydrogen like HCl or H2SO4 or something like that. We like to, as general chemists, like to put the hydrogen out front, even though that's not technically accurate for all of them. Commonly, they're bound to an oxygen atom. You'll see that in organic chemistry. We'll take a look at the formula of the acid. Right? Starts with a hydrogen at this level. We'll assume exactly 1 mole of that acid. And then we'll take a look at the chemical formula and determine from that how many acidic hydrogens, and we're going to be, as general chemists, putting those hydrogens out front to make it as easy as possible. Are there 1 hydrogen, 2, 3? The number of acidic hydrogens are the number of reactive particles you could think that that acid could release, right? And we'll look at each one in turn. So that would be the number of equivalents or number of acidic hydrogens per mole, right? Or how many moles of acidic hydrogens can 1 mole of an acid release. Gives you a nice simple ratio like a 1-to-1, 2-to-1, 3-to-1, and then we have a conversion factor to convert equivalents to moles, which we can use in a unit line equation. So let's throw up some examples of acids, show you how easy it is, and then we'll screw with our minds when we look at bases. Let's look at the simplest of acids first. We call them monoprotic, 1 proton. Remember, acids donate H+, which is technically a proton. So monoprotic acids, by definition, only have 1 acidic proton. You'll see that with the formulas. HCl, HBr, all the hydrohalic acids, HNO3, HC2H3O2. Now notice there's 4 hydrogens, but we put 1 in front and 3 in the middle. So as a general chemist, we pull the single acidic hydrogen out front, and the 3 in the middle are not acidic. They don't release. And you'll see why in organic chemistry more, maybe second semester general chemistry. But for now, it's just the number of acidic hydrogens out front. You can see the 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. Easy peasy, right? That means if I have 1 mole, exactly 1 mole of that acid, it has 1 acidic hydrogen, or 1 reactive portion, which would mean 1 equivalent per mole. For example, if I had nitric acid, I could use the formula to say there's 1 equivalent of HNO3 per 1 mole of HNO3. Some people like to put 1 equivalent of H plus or 1 equivalent of H3O plus on the top. I'm not particular to that, whatever works for you. So that is a conversion factor. So now if I know how many equivalents I have, I can convert that to moles. Or if I know how many moles I have, I can convert that to equivalents. Just like that. Any monoprotic acid is just a 1 equivalent to 1 mole ratio for that particular acid. Well, let's look at it for the next set. Let's look at, what if it has 2 acidic hydrogens? Oh, diprotic. Let's look at diprotic acids. So those, of course, have 2, or you'll hear polyprotic sometimes. Poly's generic, could be 2, 3, 4, whatever. Diprotic is 2 specifically. So this is 2 acidic hydrogen atoms. Don't overcomplicate the chemistry, guys. Most people make this a lot harder than it really is. So what are some common diprotic acids? Probably the most common would be sulfuric. Right? You've seen that one. Maybe oxalic, H2C2O4, etc., etc. That's less common. You see the 2 hydrogens there and the 2 hydrogens there? That means all of these acids, now we're making an assumption it's giving away all of those. So if it's in a scenario where it only gives away 1, then in that scenario it'd be 1 equivalent per mole. But we're going to make the assumption in this class, we're always going to react these with usually what's called a strong base that pulls all of those hydrogens off, all or nothing. If it's less than the total number, then I will give you some specific information on that. But if it doesn't state anything, just assume they all go pop, pop, and they're gone. It gives them all. Here, 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 here. So these would be 2 equivalents per mole. And if we had a specific one, let's take oxalic acid, there'd be 2 equivalents of oxalic acid, or you could put 2 equivalents of H plus or 2 equivalents of H3O plus up there per mole of H2C2O4. And that's a conversion factor between equivalents and moles. Yay! So we'll do one more, just to keep life simple. Let's do a triprotic acid. Odds are you will not encounter any acids that have more than 3 acidic hydrogens. Right? So of course I just gave the answer. Tri is 3. So we have 3 acidic hydrogen atoms for triprotic acids. Not nearly as many as those here and here. So some examples I think you might, probably the most famous is phosphoric acid. H3PO4. Arsenic acid, H3, ASO4, etc. probably some pretty crazy organic carboxylic acids that have 3 acidic hydrogens and whatnot. But we're not going to go there. Do you see the 3? 3 hydrogens, 3 hydrogens. Assuming all 3 are released, these would be 3 equivalents for every 1 mole. 1 mole of this would give off 3 acidic hydrogens. There you go. Not too bad. Let's look at, well, should I do bases? Should I cover bases first, or let's do a problem? Let's actually do a problem with this using stoichiometry and apply this conversion factor to get out of the nasty equivalents into the more comfortable moles. And then we'll look at bases, which I think are a little harder to think about because bases are proton acceptors. So looking at the formula is a little more challenging because you can't just count the number of acidic hydrogens. You have to determine how many you can pick up. So let's do an example problem to get out of the qualitative to the quantitative and then back to qualitative. Here's something you might see in a laboratory or a problem or whatever. Maybe we're making a solution, right? Let's say we make 125 milliliters of a solution of H2CrO4. What's that? Chromic acid? Or I think it's chromic acid. But 125 mils of that solution contains 0.890 grams of H2CrO4 solute. What is the normality of that solution? Now we can calculate molarity, right? Convert grams to moles, milliliters to liters, moles divided by liter, you're good to go. But let's do that one extra step and convert moles to equivalents of H2CrO4. And we'll get equivalents of the solute over liters of solution. If you're feeling adventurous, pause this video and calculate it yourself before I do. So let's go ahead and see how this looks. So what I like to do is start with we're doing solute over solution, right? So what do we know about the solute? We know the mass, so let's write that down. So we've got 0.890 grams of our solute, correct? What do we know about our solution? We know the volume. Remember, we're looking at a concentration, which is the parts of the solute over the parts of the solution. We've got grams of solute over milliliters of solution. We want normality, right? And normality is equivalence of H2CrO4 per liter of solution. Do you see that? So we need to convert grams of H2CrO4, the solute, to equivalents of H2CrO4, grams to moles, using molar mass, and then moles to equivalents using the formula. Is it a monoprotic, diprotic, or triprotic acid? Can you see it's a diprotic acid? Boom, 2 equivalents per mole. And then we got to convert the milliliters of solution to liters. That's where a lot of students forget. They get the numerator and they forget to get the milliliters and convert to liters. They do equivalents per milliliters. No. It's got to be equivalents per liter. I don't know what accent that was. But anyway, let's attack it. Now, I don't care which one you do first. Let's do the solute first. We need the molar mass of H2CrO4. So get your trusty periodic table. My friends, you probably have hydrogen memorized by now, 1.00794 times 2. We've got 1 chromium. Where's chromium? 51.9961. That's good to 4 decimal places. That's good to 5, so we're limited to 4 so far. And we've got oxygen. We got 4 of those, so 15.9994 times 4. 4 decimals. So 4 oxygens, 1 chromium, 2 hydrogens, good to 4 decimal places. So you get 118 something. So 118.0095. There's my 4 decimal places, limited by the oxygen and the chromium, right? 9580 grams of the solute per mole. No biggie, right? Let's cancel out grams of the solute. It's all unit line equations. Welcome to the meat and potatoes of chemistry. So now we have moles of solute per milliliter solution. We're not there. We got to get to equivalence. And remember, we're not solving for molarity. If we were doing molarity, we would convert that to liters and we'd be done. So let's look at H2CrO4. H2CrO4 has 2 acidic hydrogens. So let's assume exactly 1 mole of it. So if we have 1 mole that has 2 hydrogens out front, assuming they both react, we'll have 2 equivalents. And that's what we just learned with normality and equivalence. And we can now cross out moles. We have equivalence of solute in the numerator. Now we just got to get the denominator to liters. Well, it's a 1,001 ratio, so let's do that. With my limited space here, squishy. So milliliters is in the denominator, so I need it in the numerator here. So 1,000 milliliters. I ran out of room to write solution there, but 1,000 milliliters of solution per liter of solution. And I can now cross out milliliters of solution. I'm left with equivalence of H2CrO4 per liter solution. That is what we want for normality. So let me erase this real quick. Let's write our answer down. We've got 3 significant digits in the mass, 3 in the volume. Wow, 7 in the molar mass. This is exact because it comes from a chemical formula. That's exact from the metric conversion. So I'm limited to 3 significant digits. I get 0.120 vertical dash line 66 equivalents of H2CrO4 per liter solution. And that's higher than 5, right? So that's going to round up to 0.121. 21 normal. There you go. There's your brief. That's the only thing new. Just get out of equivalence to moles using the formula of the species. You're off to the races. Let's look at bases real quick and how to determine the number of equivalents per mole. And we'll do one more challenging stoichiometrical problem with a chemical reaction. And we'll be done with this video, which we'll probably watch lots of times because this is weird stuff, right? Yay! Bases are going to be harder. I think acids are pretty straightforward. Look at the number of hydrogens up front. Boom, good to go. But bases are proton acceptors or takers, right? They're the opposites of acids. Acids give H plus to bases, which accept them. So either they're being forced upon them and they're accepting them, or they really want them and they steal them from you. I'm a really powerful, strong base. I'm going to take your H plus. I'm taking your H plus. Right? Taking it away. Couple ways to look at bases in general. The way I like to look at them, because it's not obvious, they're taking H plus. Look at the negative charge, because this is H plus, right? So the negative charge can cancel out the positive charge. So for example, the hydroxide ion. This is the driving force for all acid-base reactions in general. It's the hydroxide ion from the base and the hydrogen or hydronium ion from the acid, if you're in solution, combined to form water. It's neutralization. We'll look at next chapter. That has a -1 charge, so it can only pick up 1 hydrogen to form water. That's the driving force. So would you agree that that particular species picks up 1? If I have 1 mole of this, it picks up 1 mole of H plus. So this would be 1 equivalent per mole. 1 equivalent per mole. We'll look at the carbonate ion. That has a -2 charge, so we can pick up 2 H pluses. Right, to cancel out the charge to give you carbonic acid. So this right here would be 2 equivalents of carbonate per mole of carbonate, right? And up here, this would be the OH minus. You could even do that in a compound. You could say like sodium hydroxide. Right? Still picks up 1 hydrogen. The sodium doesn't do anything, so sodium hydroxide would be 1 equivalent per mole. I could do sodium carbonate. You just ignore the cation and look at the anion. So pretty much, if we want to keep this as simple as possible, just look at the charge of the anion, and that will be the number of equivalents per mole. Let's kind of put that up here, assuming it picks up enough to become a neutral species, and we're going to assume that in this class. In the real world, what if carbonate only picked up 1 H plus? To form HCO3 minus. Well, in that scenario, it would be 1 equivalent per mole. But we're going to make the assumption that it will go to completion, right? So the charge on the anion is the number of equivalents per mole. Ho, 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 ho. We're going to look at one other type of base. These are organic bases called amines. So if you're into biology, biochemistry, physiology, you're probably more familiar with amines than pure chemists are. But those are your prototypical, what we call weak bases. These are what we call strong bases, the OH minus and things like that. I'm not worried about weak versus strong at this point. We're going to look at that in the next chapter. But let's take a look at what are called amines, which is a different way that bases can pick up an H+. So let me introduce you to amines real quick. All right, again, amines are maybe a little bit weird for you guys, but they're organic bases where the hydrogen, the H+, the acidic hydrogen, is not accepted by an anion this time. It's accepted by a nitrogen atom that has a lone pair on it. And that's what we call an amine group. You see this NH2 group there? If you put a hydrogen here, that would be ammonia. If we put a carbon-based group, that means R, that means the rest of the group. That's a carbon-based group. Oh no, organic chemistry. For the rest of the molecule, it does not matter what that is. That could be CH3, that could be C6H5, could have 100,000 carbon atoms. I don't know if anything like that even exists, but you get the idea. We just ignore that. And we see the nitrogen here with the lone pair. That's your amine group right there. And the hydrogen ion attacks right there. And we end up forming, so it's like if that was ammonia, we would get the ammonium ion. So this would give you this. And that would have a positive charge to it. Organic chemists a lot of times like to circle that. They like to circle the positive charge. It's so cute. All right. So that's how it accepts it. Right. We're not forming water or anything weird in this scenario. So I can put any R group there. It doesn't matter. And if I had, say, a second NH2 group over here, I could pick up a second one, right? But most of the amines we're going to deal with are going to be monoprotic amines, where it only has one nitrogen with a lone pair, it can only pick up one H+. So it'd be one equivalent per mole. Well, let's look at it. Let's say we have this group. Now, I'm not drawing the lone pair on there, but you can see that the nitrogen has three groups with a lone pair. So that can pick up one hydrogen atom right there. So that would be one equivalent per mole. And we can use this as a conversion factor, just like we did with the acids, to convert equivalents to moles. If I had a second NH2 group, maybe on the other side, that would be 2 equivalents per mole. Pretty simple. Right? If in doubt on this one for this class, just you see the amine group, you're like, it's probably going to be 1 equivalent per mole. But you want to look at the structure. I won't give you anything that's beyond monoprotic for amines on my exams. But homeworks and labs, anything's fair game. You never know. So pretty easy for bases. If it's an anion, look at the charge. If it's an amine, look at how many nitrogens that have lone pairs that can accept an H+. So let's end this video with a more challenging stoichiometrical problem, including normality units. And let's see how you do. It's just one extra step from what we did before. Here's your dudes a problem. This is kind of something I would expect a good challenging level for an exam. So we'll give you a reaction here. And again, next chapter, we're going to learn how to predict products. I'm not worried about that. If you don't know where the products come from, don't worry about it. We'll teach you next chapter. So we got some lead-2 nitrate solution mixed with some hydroiodic acid solution, forming this cool yellow solid, one of my favorite yellow solids or precipitates, lead-2 iodide, and then some HNO2, which is nitrous acid solution. And you get these little yellow particles floating around. So cool. What mass of the solid, the lead-2 iodide solid, can form, so that's our maximum theoretical yield. Welcome to stoichiometry. That's what this whole chapter is about, taking a reaction and converting that to a chemical equation on paper and doing mathematics or stoichiometry with it. We need concentration units if we have solutions, my friends. What mass of that solid or precipitate can form when 15.4 milliliters of a 0.8576 normal solution of hydroiodic acid reacts. So we're making the assumption that we have excess lead-2 nitrate solution, or exactly the right stoichiometrical amount, but it's probably going to be excess in the real world. And that's not molarity, my friends. That's the dreaded capital N. No, not normality. It's just one extra step, guys. That's it. Should be pretty straightforward. Let's do our game plan. Let's look at where we're starting and where we're ending. What are we solving for? Mass of lead-2 iodide. Didn't specify the units, so let's just leave it as grams. That's where we want to go. What information are we given? We're not given anything on the lead-2 nitrite. NO3 would be nitrate, so that's lead-2 nitrite solution. We were getting information on the HI. So what we're doing effectively is working backwards. Forwards. We got to get to moles of this, correct? To get to moles of that. That's true for any stoichiometry problem. Whatever you're given, whatever information is provided, get to moles of that species. Then you can connect to any other species in the mole-to-mole ratio. So we can work, so if we can get to moles of PbI2, I can just use the molar mass to get to grams of that. To get to moles of PbI2, I need moles of HI. I'm working my trip backwards this time, right? Starting with the volume, so I got milliliters of HI solution. So I'm starting with the volume of the HI solution, and I'm going to use the normality as a conversion factor. Now that's equivalence per liter, so I need to get to liters of solution, right? And then I can get to equivalence of HI. I kind of had to squish that in there. So I'm going to convert to liters because normality is equivalence per liter. And then use the normality to get to equivalence of the solute. Use the chemical formula to get from equivalence of solute to moles of solute. See the one hydrogen, one equivalent per mole. And then I can go from moles of HI, the 2-to-1 ratio of reactant to product, and then use the molar mass to do that. Do it for me, guys. Come on. Come on, man. You can do it. I'm going to pause it. I'll put this up on the board, and we'll see if we match. How'd you do? How'd you do? I ran out of room again, so I had to continue down. But let's go through the steps of the game plan, right? Take the volume of our solution, the hydroiodic acid solution, 15.4 milliliters. Let's get out of solution into solute, because it's the solute that reacts, not the solution, right? So our concentration, that's how we get from solution to solute. That's equivalence per liter, so I got to get to liters. So let's go 1,000 milliliters of solution per liter of solution. Then I can take the normality, and that says there's 0.8576 equivalents of solute, HI, per liter of solution. This is not molarity. Molarity would be moles. This is normality. Boo. All right. And we can cross out our units as we go. So I went from milliliters of solutions to liters, liter solution to equivalence of solute. And now I got to get from equivalence to moles, because I got to get to moles of this to use the mole-to-mole ratio. That is a monoprotic acid. It has one acidic hydrogen. So we're going to assume 1 mole of that acid. That has 1 hydrogen, so it's 1 equivalent per mole. It's really that easy. Just look at the chemical formula. Now that I'm in moles of this reactant, I can go 2 moles of that to 1 mole of the product I'm interested in. So 2 moles of HI to 1 mole of lead-2 iodide. Nice stoichiometry. Now, once we're in moles, we're back to our comfort zone, I should hope. And then I asked for mass, so let's do the molar mass of lead-2 iodide. So we've got 1 lead, which is 207.2, limited to 1 decimal place. 2 iodines, 126.90447 times 2. But we're limited to 1 decimal place, so I get 461.008 grams per mole, good to 1 decimal. And so when I do this whole equation, I'm going to cross out the moles there. I'm left with grams. 3 significant digits here, infinite, 4, exact, 4. So I'm limited to 3 from the volume. So I get 3.04 vertical dash line, 42 grams of lead-2 iodide. It's closer to 3.04 than 3.05 because this is less than 5, the non-significant digits. So we get 3.04 grams of lead 2 iodide precipitate. That's our maximum theoretical yield. Boom! The only difference was this one extra step going equivalence to moles. You can do this, gang!